In the video today, we're going to discuss area underneath curves and something called a Riemann sum. So first, we're going to just talk about area and how to solve what's called the area problem. So the area problem is just how do we find the area of the region R that lies under a curve f of x from A to B. So we're talking about finding the area of a very odd shape here. We're not talking about something very nice like a rectangle or a triangle that you already know how to find the area of. We're talking about just draw some function and the area underneath that function. How do we figure that out? So we're talking about this for A and this for B, and I just have some function, f of x, and we're trying to find the area of that shape there. We're going to call that whole area there the area of the region R. And we want to figure out how do we find the area of that region. And it's not just a super nice object that we can easily calculate. And the best way to do this is just to start up with some examples right away. So our first example, we're going to use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. So just to give us an idea of what this picture looks like, we have our parabola. We're really only concerned about the right half because we're going from 0 to 1. We're trying to find the area of that region down there. And we're going to use rectangles to estimate this. But before I even start estimating it with rectangles, we can already use an educated guess a little bit to get an idea of what this area is. I know the area is bigger than 0 because there's actually some area there. It's not a nothing space. But I also know the area is less than 1 because the area of this rectangle here in green, that area is 1. And I know that the area of underneath the curve is less than that. So I know I'm going to get some form of a fraction for this area. It's something between 0 and 1. But we can do way better than just estimating like that. We can get a much more precise estimation. So I'm going to use 4 rectangles on this. No particular reason, just it's a nice number to use. So I'm going to use 4 rectangles. And to do that, the first thing I'm going to do is divide my region R into 4 parts. So here's my picture again. There's my region R, and I'm going to divide it into 4 parts. Now, these parts are not going to be perfectly equal, but I'm trying to take them so that they're at least distributed pretty evenly. So here's where 1/2 is. Here's 3/4. Here's 1/4. And I've divided that region into 4 different strips. They're definitely not equal strips, but I'm dividing it equally among my x-axis like that. And I'm going to turn these strips into rectangles. And I'm going to start by choosing the right endpoint to make my rectangles. So I have one rectangle up there. There's another rectangle. And another rectangle. And our last little short rectangle. So now I have 4 rectangles estimating this area. And I can add up the areas of those rectangles. So if we add the areas of the 4 rectangles, we have an approximation for the area of R. It's not going to be a perfect estimation, and in fact, it's going to be an overestimation because all of my rectangles extend above the curve. But it will get us a pretty accurate representation. So how do I find the area of all of these rectangles? Well, I know that the bottom of each rectangle has length 1/4, just by the way I divided my interval up. I have to figure out the height of each of these rectangles. Well, the height of this rectangle here, I get by taking my 1 and plugging it into my function. The height of my next rectangle is f of 3/4. Height of this rectangle, f of 1/2. And height of my shortest rectangle is f of 1/4. So I'm getting those by plugging the right endpoint into my function. Now remember, my function was just the function x squared. So let's add up the area of these rectangles. So let me write this down again. My width of rectangles, all of them were width 1/4, and the height of the rectangles, my shortest rectangle was 1/4 squared. Next shortest was 1/2 squared. Then I have 3/4 squared, and my tallest rectangle had height 1 squared. So that means that the area, using 4 rectangles and right endpoints, is going to be area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle and plus the area of the fourth rectangle. And when I add those all up, I'm getting that this is equal to 15/32. Which, if I put into decimal form, is 0.46875. So that gives me an estimation, but I know that the area of that region is actually smaller than that. My area of S, I know, is going to be less than my 0.46875, but that's still a better estimation than just saying it's between 0 and 1, like we had just by looking at it. And I'm sorry, I was calling my region R. My area of R is less than 0.46875, but we can still do even different from that. So that was taking 4 rectangles using the right endpoint. What would I get if I used the left endpoint of the intervals instead, but still did 4 rectangles? So let's see what happens if we try it with left endpoints. Let me draw my picture again. There's one. I have my parabola. And we were dividing into 4 subintervals. So I have, here's where 1/2 was. Then I have 3/4. And I have 1/4. But instead of taking the right endpoint of the subintervals to estimate the area, I'm going to use the left endpoint. So instead of using the point all the way up here at f of 1 to estimate this last strip, I'm going to use the left endpoint of the interval and estimate with this rectangle. Similarly, left endpoint of this interval gives me that rectangle. More left endpoints, and this last one's going to be kind of silly looking. The left endpoint of this very first interval over here is at 0. So that's a rectangle that doesn't even have a height, but it's still there. I still have 4 rectangles. So this is using the left endpoints. And just looking at this picture, I can already say that the area from these 4 rectangles is going to be smaller than the area of my region because all of my rectangles are shorter than the curve. But if I estimate all of this, remember all of the widths are still going to be 1/4. And the height of all of these rectangles, well, this height is from f of 0. This height is from f of 1/4, f of 1/2, and f of 3/4. That gives me the height of all of my different rectangles. So my heights are going to be 0 squared, 1/4 squared, 1/2 squared, and 3/4 squared. So if I estimate my area using these rectangles, I get that my area of R is going to be approximately my 0 squared times 1/4 plus a 1/4 squared times 1/4 plus 1/2 squared times 1/4 and plus 3/4 squared times 1/4. And when I evaluate all those fractions, I get 7/32, which is, in decimal form, 0.21875. But remember, this was an underestimation of the area of R. We had an overestimation earlier. Using those 2 estimations, I know that the area of my region is something in between those 2 values. So I know that the area underneath that curve between 0 and 1 is somewhere in between 0.21875 and 0.46875. That's a much better estimation than just knowing it's between 0 and 1. I've narrowed down my choices. But how could I make this estimation even better? The answer to that is more rectangles. I'm not actually going to do it up here because this is very difficult to do by hand explicitly. But let's just say I happen to use 1,000 strips and 1,000 rectangles to do this. If we had happened to use 1,000 rectangles to estimate this area, and still do the same exact technique, but just with 1,000 rectangles instead of 4, I get that my area of the region is some value that's between 0.3328335 and 0.3338335. And that is a much closer estimation there. We can look at that and probably think the area is probably going to be about 1/3. And soon we'll be able to actually show that the area is in fact 1/3. And don't worry, it does not involve drawing like millions of rectangles and adding up millions of areas. We have to learn some more theory, and then we'll be able to do this without explicitly drawing out rectangles. The rectangles are good though for understanding what's going on. It's a very simple concept to understand, is actually using rectangles to figure this stuff out. So let's learn some more theory. In general, if you have a region that I'm going to call S, under the curve y equals f of x from A to B, and you want to find this area, begin by dividing S into n strips. Of equal width. So this is the same idea that we were already doing with 4 rectangles. We were using 4 strips on that. We're going to use n strips here. So let me draw a picture describing what I'm doing. Here's A, here's B, and I'm dividing this into n different strips. So let's just say here's one spot, x1, x2, I'm going to divide it into a lot of different spots. This one will be xn minus 2, xn minus 1, and I have just a bunch of different strips. Let me just put a generic strip in the middle to emphasize what I'm doing. This strip here has endpoints xi minus 1 and xi. So I'm just dividing into a bunch of different strips. I'm going to call this first strip that I turn into a rectangle S1. Then I have S2. This guy here is going to be Si. This rectangle is Sn minus 1. And my very last rectangle would be Sn. So I'm dividing it to n strips to make n different rectangles. So the width of each of these strips is given by the width of one strip. I'm going to call that delta x. It's the width of my interval, b minus a, divided by the number of strips. So b minus a over n gives me the width of one of these strips. And then I have all of these different sub-intervals, and they are divided into these xi sub-intervals. So when I divide it into these strips, the strips divide my interval AB into n sub-intervals. x0 to x1, x1 to x2, all the way through xn minus 1 to xn, where x0 is a and xn is b. And I'm going to use right endpoints. The right endpoints of the subintervals are x1, which is my a plus the width of the interval, x2, which is a plus the width of 2 of these strips. And I have an xn minus 1 is a plus n minus 1 of these strips. So I get what the right endpoint is of each subinterval by adding the width of the strip to the previous one. Then I can approximate the area of each strip using rectangles like I drew earlier. So estimate the area of the strip SI by a rectangle of width delta x and height f of xi. Then when I add up all the areas, I get that the area is approximately equal to, I'm going to call it Rn to say I'm adding up n rectangles with right endpoints. And we get f of x1 delta x, f of x2 delta x, all the way through f of xn delta x. So that looks pretty terrible, but really that's the same thing we did earlier. It's just being done generically now. Rather than just having 4 strips and 4 rectangles, I'm using a generic number n. But regardless, I'm getting the height of the rectangles by plugging the right endpoint into my function, and the width of the rectangles is the width of that strip. And now we are ready for the exact definition of the area under a curve. The area of the region S under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. That is, my area is equal to the limit as n approaches infinity of that Rn that we already defined. The limit as n goes to infinity of f of x1 delta x plus f of x2 delta x all the way through f of xn delta x. So this is just saying, to get the area of that region, we're going to divide into n rectangles, and we're going to take a limit as the number of rectangles goes to infinity. So imagine dividing into infinitely many strips with infinitely many rectangles, then you will get the exact area underneath the curve. There's nothing saying we have to use right endpoints here. You could do this exact same thing with left endpoints, or honestly, any point in the subinterval period. But it's nice to be consistent, so I'm going to be showing this all with right endpoints. Nothing changes in the theory if you switch to left endpoints or midpoints or any random number in the subinterval. You still get the areas exactly equal to this limit of all of the areas of the rectangles as my number of rectangles goes to infinity. All right. So this is very clunky notation, though. It's very difficult having to write that down all the time. So we do have another notation that we use for this called sigma notation. So our sigma notation just says that I can write this f of x1 delta x, f of x2 delta x, all the way through f of xn delta x in just one concise notation that looks like this capital sigma. That's the capital Greek letter sigma. And I have I equals 1 to n f of xi delta x. This is just saying plug 1 in for I, and then plug 2 in for I, plug 3 in for I, all the way till you get to n being plugged in, and add all of these things up together. So when I plug the 1 in, I get fx1 delta x. That was the first term I had up here. When I plug 2 in, I get f of x2 delta x. And when I plug in my very last value, n, I get f of xn delta x. So this is the same exact thing. It just avoids all of the pluses and dot, dot, dots that we had before. It makes it a nice, concise notation. So we can now say that my area is exactly equal to the limit as n approaches infinity of this sum. Just to save us a little bit of writing. All right, so that's pretty complicated, but it's not too terrible. And this is actually called a Riemann sum. It's named after the mathematician Riemann. And really, we already have it right here, this sort of definition right here. This sum right here is a Riemann sum. And we have the limit of the Riemann sum gives me the area. So let us do an example with this. But actually, before I do a full example, let's get some formulas that show up a lot when you're using these sums. So these are some formulas that you can use when you have to evaluate a sum. One very common formula is that the sum from 1 to n of I, so know that that's equal to 1 plus 2 plus 3 plus 4 all the way through n. This is exactly equal to n times n plus 1 over 2. If you have the sum from 1 to n of I squared, that's exactly equal to n times n plus 1 times 2n plus 1 all over 6. So this sum would be 1 squared plus 2 squared plus 3 squared all the way through n squared, and that equals this nice formula right here. Another common one that we see is the sum of the cubes. And that gets me n times n plus 1 over 2, the whole thing squared. Some other nice formulas that really aren't formulas as much as they are as properties or rules. If I have a sum of just a constant, so I don't even really have anything to plug those numbers into, this is just equal to n times that constant. If I have a sum from 1 to n of a constant times things that I can plug the i's into, I can pull that constant out in the front. And if I have a sum from 1 to n of two different things added or subtracted together, I can take the sum of each piece individually and add the results. All right, we're ready to actually do an example calculating the area using one of these Riemann sums. We're going to find the area under f of x equals x to the third minus 6x on the interval 0 to 3. Well, first, remember we have to divide this into n strips and get the area of n different rectangles, add them all up, and then we're going to take a limit at the very end to get the exact area. So with n subintervals, the width of each of these subintervals, and thus the width of my rectangles, is going to be delta x, which is equal to my b minus my a over n. So I have 3 over n as the width of my subinterval. Then if I'm going to get all of my right end, or all of the endpoints of my interval, I know x0 is equal to 0, x1 is equal to 3 over n, x2 is equal to 6 over n, and in general, xi is equal to 3i over n. So I get that by just adding one of these widths of the subintervals to the preceding value to get my next endpoint of the intervals. So now I have my area should be equal to the limit as n goes to infinity of the sum from 1 to n of my function with xi plugged into it times my delta x. And let's just fill in whatever we know at this point. Well, this is the limit as n goes to infinity of the sum from 1 to n of f, my xi was 3i over n, and my delta x was 3 over n. Now, using some of the properties that I had listed before, note that that 3 over n, that's a constant. It's a constant because that 3 and that n right now are fixed. I'm not changing that 3 over n when I plug in different values for I. It's always just 3 over n. That means I can pull that constant out in the front. And I get a limit as we go to infinity of my 3n, or 3 over n, times the sum of my f of 3i over n. Well, my function was x cubed minus 6x. So I'm plugging in that 3i over n into my function. And now I need to just try to simplify this as much as I possibly can. 3i over n to the third is 27 I to the third over n to the third. And this guy is 18 over n times my I. So I get a limit as n goes to infinity, 3 over n times the sum from 1 to n of 27 over n to the third times I to the third minus 18 over n times I. Now I'm just going to rewrite this using more of the properties of sums to try to get it in a form that I can actually evaluate. So I have, oops, I don't want to write that down quite yet. I have my limit as n goes to infinity, 3 over n. I can separate this into two different sums and also pull constants out. So I have 27 over n to the third times the sum of I cubed minus 18 over n times the sum of I. And now, I'm going to rewrite this a little bit more, combine some constants together. I have a limit as n goes to infinity of 81 over n to the fourth, the sum of I cubed, minus 54 over n squared, the sum of I. So what I did there is I just took my constant 3n and I multiplied it onto both of those constants, just to write it a little more concise. Now, this sum of I cubed and this sum of I, those were two of the formulas that we wrote down that come up a lot with Riemann sums. So I'm going to plug in what those values are based on the formulas that I wrote down before. And we have a limit as n goes to infinity of my 81 over n to the fourth. That sum of I cubed is equal to n times n plus 1 over 2, and the whole thing squared. And for my other guy, I have 54 over n squared, and that sum of I is equal to n times n plus 1 over 2. Now let's just take a look at this right now. We've got pretty good at doing limits over our time in Calc 1, so we should be able to figure this out right now. Think about if I distributed everything in here. Well, I would end up with an n squared plus n, and then the whole thing gets squared. So I'm going to get an n to the fourth in the numerator there. I also have an n to the fourth in the denominator. We can take the limit of that. Let me rewrite this just a little bit to make it a little more obvious what's going on. I have an 81 times an n squared plus n squared over, in the bottom I have 2 squared, which is 4, and I have an n to the fourth. And I'm going to do something similar over here. I have a 54 times n squared plus n over 2n squared. Okay, well we can handle this limit now. If I distributed this whole n squared plus n squared out, we know it's an n to the fourth. I know that when I have a limit as n goes to infinity, and the numerator and the denominator have the same degree, then I get the ratio of the coefficients as a result. So I'm going to get 81 over 4 for this first part. And over here too, I have an n squared and an n squared. They have the same degree again. So I'm going to get the ratio of the coefficients as the result. So I have 81 over 4 minus 27. And this is equal to negative 27 over 4 as the area under that curve. Now you might be wondering, but why is that area negative? Should we not have a positive area if we're talking about area? And all that means is that if you graph this out, more of the function would happen to be below the x-axis than above. So we just consider the area below the x-axis to be negative and the area above to be positive. All right, so I know that was a lot to take in for one video, talking about area under a curve by adding up rectangles and now taking limits. And it sounds very complicated, but I'm promising you, hang in there and we'll have a much simpler way to calculate these areas. We just have to learn all the theory behind it first so we can truly appreciate what's going on. If you have any questions, feel free to leave them down below, or you may ask in office hours or through email if you're one of my current students. And I will see you on the next video.